The article in question describes the process of turning a riboflavin-binding protein into a self-sufficient monooxygenase by cofactor redesign. Monooxygenases are good catalysts for enantioselectivity, which is when a molecule has the same chemical makeup but a different structure, almost like a right hand and a left hand. They can favor the production of one enantiomer over the other, which is important in drugs because certain enantiomers have different effects on certain situations. For example, one enantiomer could cure the disease, while other could cause harmful side effects. However, their use is hampered on their dependence on NADPH because it is very expensive, so a cheaper way was needed to produce the same product. Hydrogen peroxide can be used to make the same catalyst, but allows the chemical reaction to be cheaper. Here, you can see that the same starting point was used, and the chemical reaction where you had to add the NADPH to make this substance was produced the same way by adding hydrogen peroxide. The only problem was that the hydrogen peroxide alone is unstable and will break down in water. With that said, we needed to add different functional groups to the hydrogen peroxide product to make the catalyst more stable. This was done by adding, by using the selected binding protein RFBP from chickens, which has no catalytic activity, but has the capacity to bind to the different riboflavins. RFBP binds to a wide range of flavin derivatives. After reconstruction of flavins and verification of tight binding, the derived synthetic flavoproteins were tested for their ability to perform peroxide-driven enantioselective sulfoxidations. Table 1 shows the different attempts to bind the functional groups to the flavins and how much of each attempt was converted into the catalyst, the product desired, and how much sulfur oxide was in excess. Flavin number 6 proved to be the most successful, with conversion rates between 43 and 60%. Although the excess was also higher than the other attempts, the conversion rate into the proteins needed were well above any of the other flavins produced. Flavin 5 and Flavin 3 also proved to be very successful. This shows that different substances can be used to produce the same effect as the very expensive NADPH reactions and can help with drug production in the future.